Math 1314, Tyler Junior College, Section 4.1, Exponential Functions. Application, Modeling Population Growth. The last three videos in this series are going to show some applications of exponential functions. For example, the function f of x equals 1,145 e to the 0.0325x power models the population of gray wolves in the western Great Lakes X years after 1978. Before we read the actual questions we're going to answer, let's make sure we understand what we're being given here. We're given a function that takes in a value and gives us back another value. That's what functions do. But in this context, the input and the output have meaning. In this case, the input is measuring the number of years after a certain starting point. So for example, in the year 2000, that would be 22 years after 1978, so x would equal 22. But when we put that number into the function, the output gives us the population of gray wolves in an area. Now, if you're wondering, how can you exactly measure something like that hasn't happened yet? And the answer is you can't. This is an example of what's called mathematical modeling, where we take past data to create a function that fits that data in an effort to use it to try to make predictions for the future. Math models are never perfect, but we strive for perfection as close as we can. Now this model has an inherent flaw, which hopefully at the end I'll remind, well actually I'll tell you what it is right now. I know what the graph of this looks like. This base is positive, so it's an exponential growth. This would invoke a vertical stretch by a lot. This would invoke a horizontal compression by the reciprocal of that, but it would be a positive number. And so basically it's getting stretched, but it's not getting reflected, which means the graph of this would look like this up to scaling. Well, according to this, as x goes to infinity, so does the population, which means as time goes by, according to this model, the population will just get infinitely larger. So all models have flaws, but the biggest flaw in this one is it's only good for a finite amount of time. There's no way there can be an infinite number of wolves. There are things in nature that check population control, which may make you wonder, is there a better model for modeling populations? And the answer is yes, because populations tend to fluctuate based on resources, based on land, based on disease and stuff. But that would require trigonometry, which is beyond the scope of this course. But in the meanwhile, this function will tell us or try to measure or predict the population of gray wolves a certain number of years after 1978. Part A, according to this model, what was the population in 1978? Let's go ahead and answer this one. In order to get the population is the output of the function, which means we need an input. Our input is the number of years after 1978. Well, in the year 1978, how many years have elapsed since 1978? Well, none. If we're measuring how far beyond 1978 are we, and we're in 1978, and we're 0 years past 1978. So x is equal to 0, and so the population is what we get when we substitute 0. 1,145 e to the 0.0325 times 0 power. I don't need a calculator for this. Neither do you, actually. Multiplication here gives 0. E to the 0 power is the same as anything to the 0 power, 1. So that exponential expression is equal to 1 times 1,145. So according to this model, in year 0, when they started measuring the data, there were 1,145 gray wolves. And it's not a coincidence that it's the number in front. When you're modeling population, that leading coefficient often represents initial population from whenever we started measuring things, in this case 1978. B, according to this model, what was the population in the year 2014? Well, same thing, except now we have to put in a different x. And remember, our input is measuring the number of years after 1978. So if we wanted to calculate how many years have elapsed, we would have to take the current year, 2014, and subtract the starting year of 1978, and that looks like it's going to be 36 years. Let's add them real quick to make sure. Yep. So in 2014, it's been 36 years since 1978, and so our function says let's put in 36 and see what we get. 1,145 times e to the 0.0325 times 36. Let's go ahead and multiply those two numbers. Grab a calculator here. All right, 0.0325 times 36 is equal to 1.17. So this is 1,145 times e to the 1.17. And I'm going to go to the other side of the camera and hold up the one-line calculator. The display calculators are easy to use. You can look at it and make sure you're typing in the correct thing. But if you're using something like a one-line calculator or the default calculator on an iPhone, you have to be a little bit more careful when you're typing in things like 1,145 times e to the 1.7. There's a couple of ways to do it, but the easiest way is from left to right. Just remember, in a one-line calculator, when you do e to a power, you have to type the power in first. So 1,145 times, now I'm not going to press the E button yet because in this calculator I have to put the power in first, and the power is 1.17. And then say I want you to put that number on a power as E, and then press equals to complete the multiplication. So it looks like it's that, but we're going to round it to the nearest whole number since we're counting wolves. Now, if you had done it in a display calculator like this one, you would just pretty much type exactly what you see, which in this case would be 1,145 e to the 1.17. And honestly, in this calculator, I could have typed the multiplication problem up there instead of its answer. And we put it in and we get the same answer as before. So it looks like 3,689 when we round it to the nearest whole number. Let's focus. There we go. 3,689. Approximately 3,689 gray wolves. We got a third part, which kind of follows up on the idea that a model is rarely ever perfect because it's hard to predict things that are chaotic in nature. And by the way, the adjective chaotic there isn't just a random adjective. There's a strict mathematical definition to it. If you're interested, I recommend studying dynamical systems. The actual population in 2014 was 3,686. By how much did this model overestimate or underestimate the actual population? Well, the actual value was 3,686, but what the model predicted was 3,689. So the model overestimated. The model overestimated the population by, and if we wanted to see how much it overestimated it by, we could just subtract 3,689 minus 3,686, but it might have been kind of obvious that it just overestimated it by 3. And in the realm of mathematical modeling, missing by 3 on a scale of thousands is considered a resounding success. All right, so there's one example of an application. In the next one, we're going to look at an application that might be of a little bit more interest to you. It's about investing money and watching it grow.